Hello everyone, welcome to this class on finite element methods, and in this class let's learn about this analysis of beams. So a numerical problem on analysis of beams, and here we have a problem: analyze the beam shown in the figure by finite element methods FEM and determine the end reactions. End reactions means at these ends. Also determine the deflections at midspan. Midspan in the sense it's at the middle of this beam. Given Young's modulus E is given as 2 into 10 to the power of 5 Newton per mm square, and I, moment of inertia, is found to be 5 into 10 to the power of 6 mm to the power of 4. So here a beam is given for about 5 meters from the left end. We have 12 kilonewton per meter UDL, that is uniformly distributed load, and from the midspan to the end we have a UDL 24 kilonewton per meter acting for a distance of 5 meters. So here in this problem, let's keep all the units in newtons as well as in meters. So usually we keep in Newton and mm. In this problem, let's try to keep everything in newtons and meters. So because the reason is here it is in meters, so let me try to convert this into meters itself. So it will be quite convenient for me. So let me try to keep everything in meters. So here already the lengths are given in meters, and even the UDL, that is given in meters only. So this one, if I try to convert it into meters, it will be good. So Newton per mm square. So it is mentioned as Newton per mm square. So we all know like 1 mm is 10 to the power of minus 3 meters. So therefore, if I'm trying to substitute that 2 into 10 to the power of 5 newtons per, in place of millimeter square, I'll try to write it 10 to the power of minus 3 meter the whole square. The resulting answer will be like this: 2 into 10 to the power of 5, 10 to the power of minus 3, the whole square will be 10 to the power of minus 6. So if it goes to the numerator, you will get 10 to the power of 5 into 10 to the power of 6 Newton per meter square. So the ultimate answer will be 2 into 10 to the power of 11 Newton per meter square. Even this conversions is already solved in analysis of bars in my previous videos. You can go and watch that. So you can get a clear understanding of that. So Newton per meter square. So similarly here, in place of mm to the power of 4, if I'm trying to put 10 to the power of minus 3, I'm going to 10 to the power of minus 3 to the power of 4 is going to be 10 to the power of minus 12. So 5 into 10 to the power of 6 into 10 to the power of minus 12 meter to the power of 4. So 6 minus 12 will be minus 6. So it's going to be I equals to 5 into 10 to the power of minus 6 meter to the power of 4. So now everything is converted into meters and newtons. So now let me just go into the solution. So the first step is always going to be the FEA model. So the FEA model, let me try to draw the FEA model for this given beam. So the FEA model is going to be like this. So I'm going to draw 3 nodes. So 3 nodes. So node number 1 and node number 2 somewhere at the midpoint here, and this is node number 3. So this is node number 1 and this is node number 2 and this is node number 3. So at every node you have there is a vertical displacement as well as there is a angular displacement. So at node number 1, vertical displacement I'll indicate it by Q1, angular displacement I'll indicate it by Q2. Similarly at node number 2, vertical displacement Q3, angular displacement Q4. Similarly here it's going to be Q5 and Q6. So the vertical or linear displacement. So this is, and then here to here it is going to be L1. So it is going to be L1. L1 is found to be 5 meters, and from here to here it is going to be L2, that is length of element 2, which is going to be 5 meters. And this I'm going to indicate it by small e1, that is element 1, and this I'm going to indicate it by small e2, that is element 2. So this is the first step. The second step you all know, that is elemental stiffness matrix. I'm going to write it as ESM. In the exams, whenever it is asked, you can try to write the complete formula. So the formula is generally K equal to EI by L cube it is, so EI by L cube. And here this is what is very important. So it is a 4 cross 4 matrix. So first let me try to fill the numbers: 12 6 6 4. Then similarly here it's going to be 12 6 6 2, and you're going to retain the 12 6 6 2 here and 12 6 6 4. So whatever here, this and this is going to be the same, while this and this it's going to be the same. That is, on left top and right bottom is going to be the same, and right top and left bottom is going to be the same. So 12 6 6 4, and here it's 12 6 6 4, 12 6 6 2 and 12 6 6 2, because this is how I remember. I'm going to take it as 4 quarters, just like 4 parts or something like that. And here now I'm going to add here L and L square, or LE, I can just add it, length of element, LE square. So similarly LE and LE square. For the second, third and fourth elements, usually we try to add like that in every part. So LE and LE square. So I'm just going to do it like that, and here this I'm going to make it negative. So these two in vertical, and here these two in horizontal I'm going to make it negative, and here diagonally I'm going to make it negative. So I hope you understood that. So this is how you try to do it, all that. So this is how this is what is the elemental stiffness matrix. So I hope you are understanding that. Okay, now let me try to substitute all those values. The value of E is found to be 2 into 10 to the power of 6, and the value of I is found to be 5 into 10 to the power of minus 6. Actually the value of E is 2 into 10 to the power of 11 it is, it's not 6. So let me just try to, so this is wrong, it's 11. So 2 into 10 to the power of 11, the answer is 2 into 10 to the power of 11, and the value of I is, so the value of I is 5 into 10 to the power of minus 6. So and the value of L is going to be 5 and 5 for both the elements, and here also L I'm going to substitute it as 5 only. So upon substitution I'm going to get the values of, so let me just try to put K1. K1 is nothing but 2 into 10 to the power of 11, that is E, and I is 5 into 10 to the power of minus 6 divided by LE cube, that is 5 cube, and here I'm going to get it. So here the answers, once I just substitute, I'm going to get the answers as 12, 30, minus 12, 30. That is, I'm going to substitute the values of L. So 30, 100 and minus 30, 50. You can just try to put it in your calcs and get the answers. So, and here it's going to be 2 minus 30, 30, 50, minus 30 and 100. So it is just going to be like that. You can just check it out here as well. So it is not 2 here, it is 12. So here it's going to be 12. So 12, 30, 30, 100, minus 12, 30, 30, 50, minus 12, 30, 30 and 50, 12, 30, minus 30, minus 30 and 100. So that is going to be the same for K2 as well, because even in K2 the answers are not going to be, I mean the E and Y values and L values are not going to change. And once upon substituting all these in the calcs, I'm going to get it as 8 into 10 to the power of 3. So it is already found out, so I have already found out that. So let me just try to put it for K2. E value is going to be the same, I value is going to be the same, and L value is also going to be the same. So therefore it is going to be 8 into 10 to the power of 3, and this value is going to remain the same. So 12, 30, minus 12, 30, 30, 100, minus 30, 50, minus 12, minus 30, 12 and minus 30, 30, 50, minus 30, 100. So this is going to be for nodes 1, 2, 3, 4, because elemental 1 and element 2. So you can just see from the FEA model, elemental 1 means it is 1, 2, 3 and 4. Element 2 means it's 2, 3, 4, 5 and 6. So it is going to vary accordingly. So it's going to be 1, 2, 3, 4 and 3, 4, 5, 6. So 1, 2, 3 and 4. So here similarly it's going to be 1, 2, 3 and 4, and here it's going to be 3, 4, 5 and 6. So here I'm going to retain it as 3, 4, 5 and 6. So this is what you are going to write the elemental stiffness matrix. The step 3 we all know, that is global stiffness matrix. So global stiffness matrix. So let me try to write the global stiffness matrix. So global stiffness matrix, I'm going to add it. So K equal to K1 plus K2. So here you're going to get a 6 cross 6 matrix, because the maximum number of that is the number whatever I'm going to get it is 6. So 1 to 6 I'm going to get it. So it is nothing but going to be 6 cross 6 matrix. So here this 8 into 10 to the power of 3, which is common in both K1 and K2, that I'm going to retain, because here once upon solving this I'm going to get it 8 into 10 to the power of 3. Here also it's going to be 8 into 10 to the power of 3. So upon solving the answer, so you all know how to do this elemental global stiffness matrix. If you have doubts you can refer to my previous videos, where I have clearly explained how to add this global stiffness or how to obtain this global stiffness matrix whenever there are different elements. So let me just try to write the answers. So minus 12, 30, 24, 0, minus 12 and 30, and here it's going to be 30, 50 and 0 to 100, minus 30 and 50, and here it's going to be 0, 0, 0 and 0, and minus 12, minus 30, 12 and minus 30, 30, 50, minus 30 and 100. So this is going to be nodes 1, 2, 3, 4, 5 and 6. Similarly here it's going to be nodes 1, 2, 3, 4, 5 and 6. So this is going to be a 6 cross 6 matrix, as I told you. So once you finish writing the global stiffness matrix, the next thing is you have to write the global load vector. So global load vector, so already we have obtained there is a derivation on global load vector for a uniformly distributed load, for a uniformly varying load, and for a point load. For a point load it's going to be normal, but for a load, for a global load vector for uniformly distributed load. So here in this problem you can just see clearly there is a uniformly distributed load altogether, all over. So whenever you are having a uniformly distributed load, understand that the formula is going to be this, that is F equal to, let me try to write the formula, W into L by 2, W into L square by 12, W into L by 2, and W into L square, that is minus W into L square by 12. So 2 and 12, 2 and 12, WL by 2, WL by 2, WL square by 12 and WL square by 12. It's going to be plus and minus over here. And this one I have to find it for separately for element 1 and element 2, because at element 1 you're going to get 1, 2, 3, 4, element 2 you're going to get 3, 4, 5, 6. So that one you have to understand it here clearly. Element 1 is 1, 2, 3, 4 and element 2 is 3, 4, 5, 6. So always remember that, don't make mistakes over there. So for element 1, then W value is nothing but the load. This is nothing but going to be W. So this is going to be W for element 1 and this is going to be W for element 2. So understand that as well. So for element 1 this is going to be W value 12. That is, I'm not going to just write it as 12 into 10 to the power of 3. The reason is it's going to be in kilonewtons to newtons. So then L value is going to be 5 for both the elements. So for element 1, when I'm trying to write, so how I'm going to write, I'm going to just write it F1 is equal to 12 into 10 to the power of 3. So 10 to the power of 3 is common over everywhere. So what I'm going to do, I'm just going to write the 10 to the power of 3 outside. So 12 into 10 to the power of 3. And one more thing also you have to observe here, the load is acting downwards here. So whenever the load is acting downwards, always take the load value as minus. Whenever it is acting on top, in the top direction, consider it as positive. So here it is acting in the bottom direction or in the downward direction. So let me try to consider it as negative. So minus 12 into 5 divided by 2. And here it's going to be again minus 12 into 5 square, that is 25 divided by 12. And here it's going to be minus 12 into 5 divided by 2. And here it's going to be minus 12 into 5 square, that is 25 divided by 12. So 10 to the power of 3 has been common over here. So let me just try to write the answers for that. So the final answer for that is going to be, so minus 30. So minus 60 by 2 is minus 30, and here it's going to be minus 25. Here it's going to be minus 30, and here it's going to be 25. So this is what is the value of F1. So this is for the nodes 1, 2, 3 and 4. So that is, you have to understand that much clearly. So this is going to be for nodes 1, 2, 3, 4. So similarly, when I do for F2, I'm going to get it for the nodes 3, 4, 5, 6. Then I'm going to add F1 plus F2. Okay, let me try to continue writing that load vector for element 2. Load vector for element 2. So load vector for element 2. So for element 2, in the sense, I'm just going to indicate it like this. The formula is going to remain the same anyways. WL by 2, WL square by 12, WL by 2 and minus WL square by 12. So this is going to be the formula list. And here W value is going to be 24 because it is clearly mentioned in the problem itself. You can just see here that the value of W, this is going to be the value of W for element 2. So for element 2 and element 1, for element 1 it was 12 and for element 2 it is 24. It's going to be minus 24 into 10 to the power of 3 Newton per meter. So that is what is going to, and L value is going to be 5 meters. So that is L2. So now if I try to substitute it, I'm going to get this 10 to the power of 3. I'm going to take it common because it's going to be there in every element of the matrix. So final answer, I'll just try to write the final answer. So W is 24 into 5 by 12. And here it's going to be 24 into 5 square. 5 square is 25 by 12. 24 into 5 by 12 minus 24 into 25 by 12. So here it's going to be 2 and 2 here. So 10 to the power of 3, I'm going to take it common. So the final answers, I'm going to write it. It's going to be minus 60, minus 50, minus 60. So it's here it's a negative, as I told, and here it's going to be positive because already there is negative. Minus into minus, it's going to be plus. So 50. So this is for nodes 3, 4, 5 and 6. So you got the answers for nodes 1, 2, 3 and 4, and for nodes 3, 4, 5 and 6. So once you have got that, you have to write the global load vector for the combined beam. So global load vector for the combined global load vector for the beam. So for the beam, now we are going to add both. For the beam is given by. So here you can just see clearly, here it's going to be 1, 2 and 3 and 4. So here it is mentioned as 1, 2, 3 and 4, and here it is mentioned as 3, 4, 5 and 6. So now we are going to add and get it for 1, 2, 3, 4, 5, 6. So let me try to add that. So I'm going to get it. So 10 to the power of 3 is going to remain same, and 1, 2, 3, 4, 5, 6. So what do you find here? So here you find minus 30 and minus 25 at 1 and 2. So it's going to be minus 30 and minus 25. And what do you find here? Minus 30 and 25 over here. So minus 30 and minus 63 and 3. I'm going to add it. I'm going to get minus 90 and 25. I'm already having here at 4. And here at 4, I'm having minus 50. So 25 minus 50 is going to be minus 25. And 5 and 6, I'm going to retain it to say minus 60 and 50. So this is, I'm going to get it as at nodes 1, 2, 3, 4, 5 and 6. So there are only 3 nodes, but different different numbers. So at every node you have 2 displacements. For 2 displacements you will be getting 2 forces. So F1, F2, F3, F4, F5 and F6. So obviously the global nodal displacement vector, displacement vector. So that is given by, so again that's going to be Q. So Q into, let me just try to write Q1, Q2, Q3, Q4, Q5 and Q6. So Q1, Q2, Q3, Q4, Q5 and Q6. So that I'm going to write. So the next step will obviously be the equilibrium condition. So let me try to write the equilibrium condition. So that is going to be the step number 4. So the step number 4 is going to be equilibrium condition. Step number 4 is equilibrium condition. Equilibrium condition is given by K into Q equal to F. So K is the global stiffness matrix, Q is the global nodal displacement vector or the displacement matrix, and F is the global load matrix or global load vector. So let me try to write all those. Okay, I have mentioned all the K, Q and F values. That is, the equilibrium condition is clearly given like this. That is the value of K, that is equilibrium, that is a global stiffness matrix. So here I have forgot to write 8 into 10 to the power of 3. So that is K value, and Q values Q1, Q2, Q3, Q4, Q5 and Q6, and F value. F value is 10 to the power of 3 is common, and apart from that I have written this. So now I have to apply the boundary conditions. So on applying boundary conditions, I'll just try to take it as step number 5. On applying boundary conditions, I'll just try to write it BCs. So BCs are nothing but boundary conditions. So here in this problem, let me just mention you clearly. Here you can just see this is at node 1, this is at node 2, the midspan, and node 3. At node 1 it's completely fixed. Therefore I'm going to eliminate node 1 and whatever the, at node 1 you have is 1 and 2, at node 2 you have 3 and 4, at node 3 you have 5 and 6. As node 1 is completely fixed, I'm going to eliminate first row and first column, second row and second column. And at node 2, that is at node 2 you have 3 and 4. At 3 and 4 there is this, 3 is nothing but the vertical displacement, 4 is nothing but the angular displacement. So therefore 4 is nothing but the angular displacement, that is roller can go angular, obviously it can go angular like this, but it can't move vertically like this. Therefore third, the number corresponding to 3, that is third row and third column also I'm going to eliminate. Similarly at node 3, here you have another roller support, roller can move angular but roller can't move straight, that is linear. Therefore fifth row and fifth column also I'm going to eliminate. Therefore first row, second row, third row, fifth row, first column, second column, third column and fifth column, I'm going to eliminate all of them. So once I try to eliminate all of them, what I'm going to get? So let me just try to eliminate the first column. So first column I have eliminated, second column I have eliminated. So third and fifth, as I told, third and fifth is what you have to eliminate. So third and fifth, when I try to eliminate third column, fourth column I'm going to leave it as it is, fifth column I'm going to eliminate. Similarly first row, second row, third row and fifth row. So similarly here also it's going to be the same. I'm going to eliminate this as well, first, second, third and fifth. So as I try to eliminate that, I'm going to get q1 which is equal to q2, which is equal to q3, which is equal to q5, that is equal to 0. So once I have eliminated all of them, what I'm going to get, I'm going to get 200, 50, minus 50 and 100 from the fourth and sixth columns. And here this 8 into 10 to the power of 3 will remain common. And here I'm going to get q4 and q6. So q4 and q6. And here I'm going to get minus 25 and 50. So now let me try to do the matrix multiplication for both these. So 200 into q4, that is 200 q4 plus 50 q6. So this is going to be the common, that is 8 into 10 to the power of 3, that is equal to minus 25. And similarly, minus 50 q4 plus 100 q6. Here 8 into 10 to the power of 3 is going to remain same, that is equal to 50. So I have just got this equation. So once you try to go to this equation mode, so all that, so let me just try to do that. So let me first try to reset my calculator. So I have just reset, then just go to mode. So just keep pressing. So here you have equation and the number of unknowns are 2. So the value of a1 is here, this is going to be a1, b1, c1, a2, b2 and c2. So the value of a1 is found to be 200, value of b1 is 50, value of c1 is minus 25, a2 is minus 50, b2 is 100 and c2 is 50. So once the answer, the final answer, whatever I've got, I'm going to divide that answer with this 8 into 10 to the power of 3. So for both, so x value is nothing but q4. So q4 I'm getting it as minus 0.22. So divided by 8 into 10 to the power of 3, because this 8 into 10 to the power of 3 we have never considered while applying in the calc. And similarly q6 I'm going to press it equal to again, and I'm going to get it as 0.38. So 0.38 divided by 8 into 10 to the power of 3. So let me just try to find out the answer of that. So let me try to reset it. So minus 0.22 divided by 8 into 10 to the power of 3 is nothing but 8000. So let me just get it. So minus 2.75. So the final answer is minus 2.75 into 10 to the power of minus 3, and so 10 to the power of minus 5 it is. And similarly 0.38 divided by 8000 is going to be 4.75 into 10 to the power of minus 5. So q6 is found to be 4.75 into 10 to the power of minus 5. So the answer is going to be in radians. So radians, because these are all angular displacements, and angular displacements are not given in millimeters or meters, it's going to be given in radians. So this is what is going to be the displacements at the nodes. So apart from this, we also have to find the end reaction. So let me try to find that.